Okay, so the other really important operation that involves matrices and vectors is known as the rank 1 update. Now what is that? Well, here is a concrete example. It's a vector times a row vector that you add to a matrix. Now for the moment, let's just concentrate on this right here. Okay, what is this? This is also known as an outer product. It's also a 3 by 1 matrix times a 1 by 3 matrix, so the result should be a 3 by 3 matrix. And how do you compute it? Well, if you think of this as a matrix and this as a matrix, then the first element would be this times that. The second element in the matrix would be this times that. The third element would be this times that, and so forth. So notice that this represents a 3 by 3 matrix corresponding to the outer product. There's a difference between an inner product and an outer product. People get confused by that all the time. Alright? Be careful. Inner product would be a row vector times a column vector. Outer product is a column vector times a row vector. Okay? Now, if you work this out, what do you notice? You also notice that the first column of the result really is just this vector here times that element right there. See that? Second column is this times that. This times that. And now we understand where the term rank 1 comes from. This is a rank 1 matrix. Why? Because each column is just a multiple of each other column, so there's only one linearly independent column, if you remember that terminology from linear algebra. If you don't panic, you'll be okay. Okay, so notice that what we just said can be summarized as the first column is just this vector times 3. The second column is just this vector times -2. And the last column is just this times -3. Okay, now notice that we want to add this to a matrix. So notice that then corresponding elements must be added together. So if we add A to this, what would we get? We would get plus -1 plus 0 plus 2 plus 1 plus -2 plus 3 and plus -3, -1, -1. And the same thing down here. What do we notice? Let's focus on a typical entry in the result. What do we recognize there? It's a scalar times a vector plus a vector, but if we overwrite this matrix with the result, it even overwrites the original vector there, the same vector. What is that? That's our good friend, the Axby operation. Okay. So how do we now come up with a partitioned matrix expression for this? Okay. What do we have? We want to do A becomes x, y transpose plus A. Okay. As a post condition, we write that as A is equal to x times y transpose plus A hat. So that's the post condition. Seems to me here that we were thinking in terms of partitioning by columns. So, certainly when we look at it that way. So let's see what happens if we partition A into a left part and a right part. Okay, well that means that A hat is also partitioned into a left part and a right part. Okay. because really that refers to the same matrix as that because it's being overwritten. And what do we now need to do with X? Well, if we do X, Y transpose, we can't add them to pieces here. We want to somehow take this and partition it by columns as well. And the way you achieve that is to say, let's do X times the vector Y split up into a top part and a bottom part. Why? Because then when you transpose that, it ends up being split into a left part and a right part. And if you now multiply that out, you get, it needs to be a plus there, you get X times Y top transpose for the left part, Y bottom transpose for the right part, plus this right here. And if you multiply that out, then you get X times Y top transpose for the left part, and X times Y transpose bottom, right there, for the right part, which you have to add to that. And if you then add it to that, then you get this right here. With a hat on here and a hat on there. And what is that? That is our partition matrix expression. And you can take that and you can come up with an algorithm. But what did we learn from matrix vector multiplication? There we could partition the matrix by columns, or we could partition the matrix by rows. Here we've partitioned the matrix by columns. I wonder if there is a second partition matrix expression that comes from partitioning by rows. Why don't you work it out? See what you come up with. All right, go to it.